let's compute the surface area of a sphere of radius a. So that's x squared plus y squared plus z squared equals a squared. And we're going to compute this using the formula we got. So what you should draw is a sphere. So here's a sphere. Its radius is a, so we'll just write that is a. And then I've got, here's my x-axis. Over here I've got my y-axis, and vertically I've got my z-axis. So in order to find the surface area, I think, we only have a formula for surface area of graphs of z equals f of xy. So I'm going to take first a restriction to z being positive so that I can solve for this as a squared minus x squared minus y squared square root. And so what I'm doing is restricting to the upper half of this hemisphere. And now I'm just going to find the surface area for that and double it. So my answer should be 2 times the surface area over something we'll figure out in the xy plane of the square root of 1 plus, and now I need to compute fx squared, fy squared, and then I've got my choice of dx or dy to use first, or some other dA. So, already, this looks kind of like I want to use cylindrical coordinates probably to compute this, because I've got, polar coordinates in order to compute this, because I've got an x squared plus y squared here. And so I see that as an r squared, or here it's a minus an r squared. That would make my life a little bit easier. A here is a positive constant, in case that was not clear. So let's compute fx and fy, and then we'll figure out how to do the polar coordinate things. So fx, so I've got that square root. If I take the derivative, so this is f. X and y. If I take the derivative with respect to x, I get minus 2x over a squared minus x squared minus y squared to the 1/2. So that was a square root to the so what was stuffed to the positive 1/2 became stuffed to the negative 1/2 times a half, and then times my chain rule term minus 2x, and that simplifies. That looks like minus x over the square root of a squared minus x squared minus y squared. And fy is similar, so I've got a big to the negative, I've got a big square root, so that's a 1/2, 1 over the square root, a squared minus x squared minus y squared, and now my chain rule term is going to be minus 2y, so the 2's can cancel, so minus y. Great. So, and the region I want to integrate over, this D, is going to be this region here in the xy plane, which looks like a circle of radius A at the origin. So we know how to express that too. Okay. Now, because D is a circle, I think, and I already can sort of see how to translate my integrand into polar coordinates, I'm just going to go ahead and do that at this point. So let's go polar. Let's go full polar. So what I want to compute, the surface area of the whole sphere, it's going to be 2 times this integral, and I'm going to go full polar on it. So my integrand is 1 plus, fx squared. Fx was minus x. X in polar is r, so minus r cosine theta. And down below, I've got square root of a squared minus r squared. Similarly, for fy, I've got minus r sine theta up top, and the square root of a squared minus r squared on the bottom. So when I square things, my life gets even better. I've got an r squared cosine squared theta over a squared minus r squared. Just over a squared minus r squared, as I said, not as I wrote, because the square root gets rid of it. Plus, for the y guy, I get r squared sine squared theta over a squared minus r squared. So, really want to emphasize this squaring I've highlighted really plays an effect on your integrand. And my dA term is now going to become r dr d theta. And I'll fill in my bounds for the disk. So theta is going from 0 up to 2 pi, no surprises there. And r starts at 0, and it's a disk of radius a, so it goes up to a. Again, a is just some constant. Okay, let's roll ahead with this integral. I see a sine squared plus cosine squared, so I'm gonna, let me highlight that. Got cosine squared plus sine squared, and everything else that they are multiplied by is the same, so I can factor that out and cancel it to make a 1, which gets rid of all the thetas in this integral, which is fantastic. So let's see what that becomes. So I've got, let's just write this integrand. 1 plus those two combine just to give me 1 r squared over a squared minus r squared. I'll close my square root. Let's get rid of the rest of this. R dr d theta. I want to be clear what's inside the square root versus what's out of it. And that should be all integrated, r from 0 to a, and theta from 0 to 2 pi. And finally, I multiply by 2 to get my surface area. And now I'm going to combine things into one fraction on the inside there, and hopefully that will make my life a lot better. And I think it is. So I get theta goes from 0 to 2 pi, r goes from 0 to a. If I combine fractions there, I get a squared minus r squared plus r squared in my numerator, so I just get the square root of a squared over a squared minus r squared r dr d theta. At this point, I would just absolutely pull out the a squared. A is positive, so I can take a square root and get a. Oh, and I forgot my 2 in front. So I'm now getting 2a, just a big constant, right? Theta goes from 0 to 2 pi. R goes from 0 to a. What I'm left with is the square root, so I'm just going to write it this way, a squared minus r squared. It's in the denominator, it's the only thing left with a square root, times r dr d theta, and that is definitely as clean as I'm going to get it before integrating. So my integral at this point, I should do a little u sub, so a squared minus r squared is going to be u. So du is minus 2r dr. And so if I put minus 2 here, I have to also divide by minus 2 outside. And so that gives me a minus a. Integral theta goes from 0 to 2 pi. Let's just totally switch over into u coordinates. So if r is 0, u is a squared. And if r is a, u is 0. It's okay that those are maybe backwards. That's fine. It's accommodated for by the negative. And this is u to the negative 1/2. du d theta. And we're rocking and rolling. That is u to the positive a half times 2. And out in front, I've got this minus a. So this is my integral with respect to u. Since these integrals are both with constant bounds, there's no thetas on the u bounds, I can just do them separately. So the u integral gives me u to the 1/2 times 2. The derivative of that is in fact what I wrote. That's good. My say out front, u goes from a squared to 0, and then that's going to be multiplied by theta from the d theta, integrated from theta equals 0 to theta equals 2 pi. So my final answer is, so minus a. If I evaluate at 0, I get 0. So 0 minus 2 square root of a squared, so 2a, and then 2 pi. So it looks to me like I've got minus, so 4a squared pi. Which agrees with, like kind of the classical formula for this, which is 4 pi r squared for the surface area of a sphere, and the volume is related, is 4/3 pi r cubed. And these are always easy to remember because there's this, you take a derivative, ddr, to go up towards the other one. So that's that.